Okay, so to help you guys out a little bit with a couple of questions that were on the lab, I decided to make a quick little presentation just to help out. The two that I had in mind were question number 6 and question 10. So here with question number 6, we're given a couple of different variables. So first off, you can see that these following measurements were made on a normal subject. So in 1 minute, they were able to breathe 9 liters in and out of their lungs. So that means for this particular person, 6 liters of that air was able to get into their alveoli where it could actually be exchanged. This person was breathing at a rate of 15 breaths per minute. So basically what this question is asking, if we go on to the next slide, you'll be able to see that it says which of the following breathing patterns would not change the subject's PaO2. So in order for it to not change, this person needs to have the same alveolar ventilation. Now to do this, we're going to have to do a couple of different things. As you can see here with A, B, C, D, and E, we're given tidal volumes and we're given frequencies. Those are breaths per minute. So we're going to first figure out something called dead space. So if I can, I'm going to go ahead and write on this a little bit. And we're going to calculate dead space. So the way you do this is you get this minute ventilation here, which is 9 liters. Sorry, this may take me just a little bit, just because I'm using a mouse. So that's per minute. And we are going to divide that by, or multiply that by 1 minute over 15 breaths. So that'll cancel out our minutes, and this will give us how many liters per breath that we have. So this will equal 0.6 liters. So in every breath that this person breathes, 0.6 liters or 600 milliliters are coming into the lungs. Now we're also going to have to do pretty much the exact same thing with alveolar ventilation. Now I'm just going to take a quick shortcut here and just do 6 liters divided by 15 breaths. Now just keep in mind that 6 liters per minute, and for every minute you're breathing 15 breaths. So that's just a quick little shortcut that I'm doing there. And that will equal 0.4 liters. Okay, so we know that every breath that this person breathes, 6 liters, or 0.6 liters are getting into the lungs, and 0.4 of those are actually being exchanged. Or the oxygen in that 0.4 liters is actually able to exchange with the alveoli air in there. So if you subtract these two values, you'll get something that is called dead space. I'm just going to do dead S just because I don't feel like writing the whole thing. But dead space. So for this, if you minus the total air that this person is breathing by the air that can actually be exchanged at the membrane level, that is going to be 0.2 liters. Now that 0.2 liters is air that is always going to be in the lungs. And really, it's not doing anything. It's not going to help increase the arterial PO2 pressure. It's really just stale air that's just sitting there. And this dead space is going to be the same no matter what this man's breathing pattern is going to be. So if we move on here to this next little slide, where we're given 5 different options, and the question is which of the following breathing patterns would not change the subject's PO2. So in other words, which of the following breathing patterns will have the same alveolar ventilation of 6 liters or 6,000 milliliters, because in here you can see these tidal volumes are given to you in milliliters. So I'm going to put that up here at the top, that our goal is to have, okay, so up here at the top I'm going to put 6 liters is our goal. I'll just do a little star. Woo! Just like that. Okay? So the way that we're going to calculate this whole thing is we're going to use these tidal volumes here. That's what this VT is, of 400 milliliters. That 400 milliliters is the same thing as this 9 liters that we had over here that turned out to be 6 milliliters per breath. So instead, with this breathing pattern, he's inhaling 400 milliliters at a time. So we'll go ahead and write that on here. So 400 milliliters per breath. And if you subtract that by the dead space that we had up above, which was 0.2 liters or 200 milliliters, that'll give us 200 milliliters of the alveolar ventilation. So I'm just going to put AV for alveolar ventilation. If you multiply that value by the frequency, so every breath he's breathing in 200 milliliters, and he's breathing 30 times per minute. So if you multiply that by 30, that is going to equal 6,000 milliliters of air that is going to be exchanged at the alveoli. So this breathing pattern, this number A, will have the exact same breathing pattern as we saw with the baseline readings that we got here, which was 6 liters, and here we got 600 milliliters. So you're going to be pretty much do the exact same thing with B, C, D, and E. And just so you know, this often comes up in tests and in quizzes, so be sure that you understand some of those processes that I was telling you about. Be able to convert from dead space to the alveolar ventilation and the tidal volumes. That's extremely important, and remember that the dead space is going to be the exact same no matter what the breathing pattern is. There's going to be more than one answer, including A, that will be correct out of all of these here below. So that's number 6 that I wanted to talk about. And the last one that I was finding students were having a hard time with was question number 10, and in particular, mostly just reading this table. It's kind of a weird table to figure out. But here on the x-axis, we have the lung volume after the person has already inhaled, and the expiratory airflow, or the air that is leaving per second. So this is just an expiratory airflow. That doesn't mean that this is inhalation, that's exhalation. No, that's not what it's saying. This entire thing is exhalation. So this person has already breathed into their max as much as they could, and then they tried to let as much out. Okay, so with this normal individual, you can see that their exhalation airflow shot up to this point, and that's the quickest the air was coming out of their mouth. And then it slowly started to kind of level off all the way until they got like 0.9 liters of air left in their lungs. So that's the normal value. I hope that kind of helps you understand how to read the table for these other two. I know this one can be just a little bit confusing. Now, the question here is asking what type of pathological things are happening here. Now, I'm not going to give you the answer, but I wanted to make some distinctions for you between the two pathologies. And that way you might feel a little bit more confident when you answer these, so you can get the whole problem right. And that is going to be obstructive versus restrictive lung diseases. So first I'm going to talk about this restrictive here. So we'll first talk about that one. So restrictive lung disease is really anything that does not allow you to get the proper amount of air into your lungs, or it makes it harder for you to breathe in. Now this can be due to many things. It could be due to scarring or a few others, but the main thing here is that the lungs are not being compliant, or their elastance is kind of gone. So when you're looking at an alveoli right here, normally when you're breathing in and out, these would be able to expand or contract. Expanding when you're breathing in, contracting when you're breathing out. And that's really what's causing air to come in and out of your lungs here. Now with the restrictive lung disease, oftentimes due to scarring, you will not get this. These will not be able to go in and out, and thus air will not be able to come into the alveoli or back out. So oftentimes these individuals will have a very low lung capacity, and it can be very hard for them to have. One example that our lab gives is pulmonary fibrosis. If you're interested, and you can look a little bit more about it, but it's basically just scarring that has occurred on the lungs. Now this last one here, which is obstructive lung disease, this has, I like to look at as it's dealing a little bit more directly with the air pathways and with the alveoli themselves. So with an obstructive lung disease, it's really easy for the person to breathe in. I shouldn't say really easy, but they can breathe in just fine, and the air will be able to come in. But then when they try to exhale and that air tries to leave, these walls will collapse, and it'll make it hard for this individual to be able to exhale. So over time, as this person inhales and tries to exhale, this alveoli will start to get larger and larger, and they will have a much larger volume of air within their lungs. So when you come back to think about these two problems, I hope that helps you out in determining which one is restrictive or obstructive. I hope this helped. If you have any questions, you're welcome to email me, and I'm sure Brother Shaw and Brother Hunt are more than welcome to help you as well. But I hope this helped, and good luck on your write-up and on the quiz next week.